Welcome, smart coder. How are you? AKSR, how's it going? Okay, let's get started with the weekly contest 387. This was not the hardest contest. Super thrill. 4-4 is a big win, a big dub. Yes. So let's not get ahead of ourselves. Let's start with Q1. Yeah, it was on the easy side. If you're gonna do virtual, then maybe you don't want me to spoil them for you. Hey, BetSim, thanks for the follow. Okay, so let's start with Q1. Distribute elements into two arrays. Part 1. You're given a one-index array of distinct integers, nums of length n. You need to distribute all the elements of nums between two arrays, array R1 and R2, using n operations. In the first operation, append nums1 to R1. The second operation, append nums2 to R2. Afterwards, in the ith operation, the last element of R1 is greater than... Why is it one index? There's no reason in this case to make it one index. Anyways, so the final result is formed by concatenating arrays R1 and R2. Return the array result. Okay, so here there is no decision to be made. So each operation depends on whether the last element is greater or not. So we can just simulate it to confuse beginners. Yeah, maybe. So we can just simulate the process. So we're told that first we put numbers. So there are at least 3 elements. So we can do this. So we create R1 with the 0th element, R2 with the first for the element 1, and then we go over from the second element, and if the last element is greater of R1 is greater than the last element of R2, then we append nums of I to RA1, otherwise we append it to RA2, and then we return the concatenation. So we get the examples right and accepted. Okay, so I'm gonna try to do this quickly. I don't think there's much to say. Hey Kevin, how's it going? Welcome. I don't think there's much to say about this one. So yeah, you would think that question 4 is the same thing but bigger, but no, it's a different problem. So it didn't pay off to do Q4 first and reuse the code because the code is different. Okay, so Q2. So counts of submatrices with top left element and sum less than k. Return the number of submatrices that contain the top left element of the grid and have a sum less than or equal to k. Okay, so it's weird how it is explained, but yes, you have to consider all the rectangles. Yeah, where the top left corner is the top left corner of the matrix. So here the size of the matrix is 1,000 squared at the most, and so we can consider all of these rectangles, but then we cannot go over the rectangle to make the sum because that would be too slow. So maybe we can do something to compute them quickly. So what I did was, let me turn on my tablet. So let's say that here you have the matrix. So this is R1, 2, and R. Yes, it would have been different. So, and here you have 0, 1, and then some C here, and so on, and then C, capital C, and capital R minus 1. Okay, so let's say that we want to know the sum of this rectangle here that is determined by this squared. So what we can do is, if we already have, so we're gonna go over all the columns from one by one, and so if we already have the sum of this squared, then we only need to add the sum of this column, of this prefix of a column, and we sum these two things and we get the sum of the whole thing. Then when we move to the next column, we do the same. If at some point we have a number, we have a sum that is greater than or equal to k, then we stop, because when we are we're growing C, so we are growing the rectangles, so there are no negative values here. They're all positive, so the sum is going to increase. So what we can do in order to have this, the red prefix of a column, we can do all the prefixes. We can have a matrix with all the prefix sums of all columns, and then we're gonna have what we need. So let's do that. So here I usually like to define the sizes as capital R and capital C. So we're gonna have the prefixes of the columns. So initially we have this. I mean, we're not gonna use this. Then the first row is going to have the first row, because that's the prefix that has only one element, and then we can go over from the second row, and for each column we want the prefix of the current row and column to be the prefix of the previous row plus the element in this cell. And so now we have the prefixes that we want. We're gonna count how many submatrices there are. Okay, so here we're gonna keep track of the current sum. And now we're gonna do this. So in cur, we already have the sum of the previous rectangle. So now we want to add the next rectangle, which is going to be the prefixes R and C. And if so, this must be, we want to count, then it's only, since all the numbers are non-negative, then it cannot decrease, so we can stop there. And here we count, if it is less than or equal to k, then we found a rectangle and we counted. Super space efficient. Yeah, I guess. Error. Where is my error? Line 8. List assignment index out of range. Oh, here I forgot to multiply by the columns. Okay. All right, so we got the examples right and accepted. Yeah, you got it, Kevin. All right. So this is all there is to it. I maybe there are other ways of doing this. Like sometimes you can do some kind of dynamic programming where you add the, so if you want the rectangle that has a corner here, then you can add the sum of this rectangle and then the sum of this rectangle and then subtract the intersection, which is this rectangle. Maybe you could do something like that as well. I think the prefix sums, it's a simpler way of doing it. All right, so let's move on to Q3. So minimum operations to write the letter Y on a grid. So this is a little complicated. So you have a grid of odd size. So it's a square grid, but the side is n, which is odd. And it can have only 3 values, 0, 1, or 2. And you want to know how many cells you have to change in order to have the minimum number of cells that you have to change, so that you have a Y written, like you have this, this. So the ones that are bold are the ones, the cells that that form the Y. And it doesn't matter which color, so the Y has to be of some color and the background, the non-Y, has to be of some different color. Okay, so it's pretty straightforward. Okay, so notice that you could try to be clever here and say, okay, so I count how many there are of each kind inside the Y and then outside of the Y, and then I see which one is the which one occurs, has the highest frequency, because that's probably the color that I want, so that I don't have to change as many. But you can just forget about that. You don't have to be clever. You can try. So there are only a few combinations, right? So for the background color, we have 3 options, and then we have 2 options for the Y color. So there are only 6 combinations. So we can try them all. So color 1, let's say space efficient. Let me see this. Is that for Q2? So here, no, we have 3 colors, and here this is going to be also 3 colors. So let's say C1 is the color of the Y, and C2 is the background color. So if they are the same, we skip it. And now we know what the color should be. So now let's go over all the cells, and we want to know if it's inside the Y, okay? Because if it's inside the Y, we know we want to color it C1. So we're gonna count. So here, the current case, for the current combination, we want to add 1 if the grid in that cell is different than the color of the Y. And if it is not, then it's the same bet with color 2, because we want to paint the background in color 2. So here we get the minimum. We update the minimum. We initialize it to infinity, and we return. So now the only thing that's missing is this function that tells us if we are inside of the Y or not. So notice that there are 2, depending on the row, there are 2 possibilities. If we are at this part of the Y with the diagonals, or if we are at this part of the Y, which is simpler. So let's say that if it's less than n divided by 2, we're at the diagonals part, and here the column must be in the middle. And if we are at the diagonal, so remember how we check if we are in the main diagonal, that means that the difference between the row and the column is 0. So notice if we are here, in a diagonal, when we move to the next element, we add 1 to the column, and then we add 1 to the row. So they cancel out. So when we move through the diagonal, so the main diagonal, the difference is always 0. But we could also be in the other diagonal. How is the opposite diagonal? And in that case, the sum, so here for example, the row is 0 and the column is n minus 1. So their sum has to be is as n minus 1. And if we move along here, we subtract 1 to the column, but we add 1 to the row. So the sum stays constant. So that's why this works. So we get the examples right and accepted. Pretty easy. So these things come up usually to know. So notice that this is the main diagonal, but if you change it, you can characterize every diagonal. Okay, so let me share this. Okay, so let's move on to Q4. So here, so this is similar to Q1, but not quite the same. So here, the operations are different. So we also start adding elements to array, so distributing the elements between array 1 and array 2. But it depends on the greater count. So we need to count how many elements there are greater than nums of I in array 1 and array 2. And we have this condition: if it's greater, then it goes to array 1. If it's less, then it goes to array 2. And if they are the same, then we break the ties on the number of elements, if the lesser number of elements. And if there is still a tie, we add it to array 1. And the result is the same as the concatenation of both arrays after we've done all the operations. So there's not much to this problem. So the key here is to find a quick way of doing this count. With in a data structure that supports. So we're going to be adding elements to the data structure, and then we're going to be making queries of the greater count. And there is in Python, or well, there are alternatives in other languages, but in Python you have a sorted list, which is not part of the standard library, but it is available in LeetCode. So from sorted containers, import sorted list, and that can help you. You can do a bisect operation that gives you the index of the element that is greater than. So that would be bisect right. That is greater the smallest that is greater than the value that you're passing, and that gives us the operation that we need to solve this. So again, we have an array 1 and an array 2 that start with the first two elements, but we're also going to have, so we're going to add it to both. We're going to have a redundant data. So here we want to create a sorted list, which initially is the same as, well, it's going to be the same as the arrays all the time. We're going to maintain that. So now we start from element 2, and we want to, so the count 1 is going to be, so if we do bisect right, like I said, we get the index of the element that is greater, the smallest that is greater. So then we subtract it by the length. So we do this calculation, and we're gonna get how many there are that are greater. And the same for S2. And so, and now we just check the condition. If C1 is greater than C2, or if they are the same and the length of array 1 is less than or equal to the length. So notice that here, if they are the same, we're going to add to array 1, which is what we are told to do. And we also want to update the sorted list. And otherwise we do the same bet for array 2 and S2. and then we finally return array 1. That's array 2. Okay, we got this right and accepted. So yeah, there's not much to it. So I promised Smart Coder to do this with a segment tree. So in case you don't have access to the sorted list, you could use a segment tree. But you need to yeah. But we need to do something. So remember that the interface of the segment tree is just an array that has range operations. But here the values are up to 10 to the 9, so they are quite big. So we need to do what is called index compression, which is just a fancy name for assigning an index to each different value, each unique value, so that they preserve the order. So the minimum value will get the index 0, the second minimum is going to get index 1, and so on. So now we're going to have a range that starts from 0 to the number of unique values. And you can do that in just one line in Python. By this, so we want the unique values. We want them sorted. And we want to enumerate them so that we assign an index to each, and we want to create a dictionary from the value to the index. So now we can convert from the value of nums to an index. Okay, and so I'm not gonna go over, so I have a video of segment tree that you can check out. I'm not gonna go into the details here. So if it's less the base, we want to multiply by 2, and we create the tree as 2 times the base, and then we want to be able to add a value. So we add 1 to this value, and then we update the parents, and we move up the tree, and then we have the other operation, which is the count of elements that we have from left to right, inclusive, and that's going to be, so we have to add the base here, and if L is odd, we want to add this, and if R is even, we want to add this, and then okay, so now we have a segment tree, and so let's do some helper functions so that we don't have to deal with the details of getting the index and so on. So we're gonna need 2 operations, right? Adding and doing the greater count. So on the one hand, we have a segment tree and a value, and we want to add it, so that's just segment add and the index of x. That's all there is to it. And then the greater count of from some element x, it's going to be s count from the index of sx plus 1, and here we want the index of the last element of the last value. So we want the sum in this range. Okay, so that we count how many there are that are strictly greater than x. And so now S1 is going to be a segment tree of size of the number of indices, and segment S2 is going to be the same, but in S1 we add S1 nums of 0, and we add to S2 nums of 1, and here we want the greater count of S1 of nums of I and the greater count of S2 of nums of I, and this is the same, and here we're just adding this, and here we're adding this, and this should work. Maybe not. So for in enumerate, here int object, this is not base, what the hell, tree and tree. Okay, so we get it right and accepted. All right. Yeah, I don't think I shared my solution, the other solution, but in any case. So yes, I coded the segment tree a bunch of times from scratch, so that's why I have it. I know it by heart. But I understand it. That's why I can code it this quickly. The count method. So index compression is just so I explained a little bit. So you have nums. Okay, so nums is an array that has values, I think, let me check, from 1 to 10 to the 9. So yeah, maybe you have a 9 and a 608 and then 1 and then maybe 10 to the 9 and so on, right? But the segment tree is essentially an array. You index, so you need to store values from 0 to n if the segment tree is of size n. So it's just an array. So you cannot index by this big number here. You need to have a range that starts from 0. So what we do is so maybe here you have another 1. So what we do is we process nums so that we remove duplicates and we sort them. So now here, let's say that we have, after we sorted, we have 1, and then we have 9, and then we have 608, and then we have 10 to the 9. So notice that we ignore the duplicated 0, and then we map it. So we do a one-to-one mapping starting from 0. Then this becomes 1. Then this becomes 2. Then this becomes 3, and so on. And so now we use these numbers, and notice that it doesn't matter that they are different because we only care about the order. And notice that the order is preserved here. So we have this relationship that is preserved here. So if we want to know how many elements are greater than or equal to 602, it's the same as asking whether how many there are greater than or equal to 2 in the indices. And it's just one line to get the mapping in Python. You remove duplicates by adding them to a set. The Fenwick. No, so I usually recommend to just learn segment tree and don't pay much attention to Fenwick tree. So because segment tree is more powerful, so I think you can do everything that the Fenwick tree does, you can do with the segment tree and some more. So I would recommend you to focus. So yeah, segment tree has some advantages. So I think the code is shorter, and it's a little bit more efficient in terms of space and time, but not in complexity, just in the constant. But you usually don't need that difference. So it's a minor difference. So I would recommend you to just learn segment tree because the code, in my opinion, it's easier to understand. If you go over my video where I explain it, you'll see this is easier to understand because the Fenwick tree depends on some bitwise operations that are not very easy to understand. I think at this point I forgot about it. No, sorted list, I think it's a skip list if I'm not mistaken. So I read a while back about how it is implemented, and it's not. So usually this kind of order statistic tree where you have this kind of operations is, by the way, welcome Midnight Simon. So usually this kind of operations are done with a binary search tree that is balanced, but in the case of sorted containers, they have different implementation. But yeah, I'll have to read up on that. I don't remember the details. But yeah, maybe if you have this as a template, then maybe you can copy paste it and it will be quick enough. But you still have to do this kind of transformation where with the sorted list is just more direct. For the count, you're not checking any individual elements. So you mean for this? So I I'm gonna share when I upload this to YouTube. I'm gonna add in the description the video, the segment 3 video, where you can dive into this code where I explained it. So you are, so you understand what the interface is. So it gives you, so we are counting. So again, this is just like an array where you add 1 for, so you add 1 to value x, and then you can ask for a range from L to R, how many values there are in that range. But yeah, if you want to dive deep, then I'll share the video. So yeah, I mean, this was it was an easy contest, I think. That's all I have for now. So, but let me know if you have some requests of streams. So Smart Coder, if you want me to review some data structure. So for in the case of Fenwick tree, like I said, I don't think it's worth it to learn it. But if you insist, I might do a stream about it. A request form. So I can create a. Yeah, but I'm thinking more about requests offline. Because if you ask me to explain Fenwick tree, I need to review it a little bit beforehand. But I can prepare a stream about it. So you can make requests on the Discord servers, on my server or your server, and I can prepare something. So yep, that's all I have. So thank you for your support. Okay, I'll think about it. Thank you. Bye bye.